Dr. Christian Jorgensen, and this is Jerry Oluwasegun.
Yeah.
Jerry is an EMRA student, and we're going to explain today molecular dynamics simulations with an emphasis on GROMACS. So after these tutorials, you'll get basic knowledge of molecular dynamics, simulation steps and how they work.
Yeah.
What's the second?
And we will talk about the basic. We are going to introduce you to like the basic GROMACS scripts, and we show you the purpose of what the script does and how it works.
And then the third is how to approach and solve issues that might arise from performing molecular dynamic simulations in GROMACS. And then
we talk about the basic analysis you can do after you get your solution installed in GROMACS.
Okay. All right. So what is molecular dynamics? So you've already had the other presentations where I covered Monte Carlo and molecular dynamics and in general the basics of NAMD and GROMACS. And in this tutorial, we're going to really delve into GROMACS and molecular dynamics. So it's a method by which we solve the trajectory of a system by integrating Newton's second law, which you have here, F equals ma. Let me just get the laser pointer. Have that here, right? And then Jerry has kindly presented here an image of your energy surface along a parameter. And here you have the system kind of sampling these two wells, right? So for instance, Jerry, you want to talk about the peptide?
Yeah, so the peptide simulation is a simulation I did with the patients during my time here. And what we tried to do was we tried to look at the conformation of pain, which is a protein of interest, across like a long simulation time. So we compared being water
so this thing is over here, right?
Yeah.
And then what's happening as we cross?
So what happens for the being peptide was it augments. So we saw like at high energy, there was like there was a relaxation of the bonds,
yes,
which caused like the alpha helices to.
And this is through molecular dynamics, guys. So molecular dynamics, you might start with your minimum energy state here, say this state A, and you can then, through integration of Newton's second law, and by chance, you can sample other states. For instance, this B to C state, which is actually a lower energy state. So actually, this might be the other way around. In this diagram, might be actually this one, sorry, and then this transitions to here. But in general, the word here is dynamics, guys. So unlike the other tutorials that I've covered with the students, this is a tutorial about dynamics. This is actually the only tutorial about dynamics. So the students here at Portsmouth, they get too much information about static stuff. And so this is why this is a very important tutorial, because then what do we have here?
You can see on the left, we compare like the molecular dynamics results to in vitro studies of measuring like the alpha helices, and you can see there's a clear correlation.
Yes, there's a clear.
So yes, the bars, circular dichromacy, and the dots are for everything. So there's a clear correlation.
So again, this is using molecular dynamics. So molecular dynamics is very useful because it can be compared to experiment. Okay. All right, let's see how I go there. Okay. Now, what is steps? So in the previous tutorials, we've covered the protein data bank. We've covered homology modeling with AlphaFold. There are no dynamics in any of those tutorials, okay? Now we're going to look at how you take your initial state that we set up in previous simulations, tutorials, sorry. But in previous tutorial, we also covered charm GUI, right? And now we're going to take that charm GUI output and we're going to give the atoms an energy kick and then move it in time. So molecular dynamics can be carried out within different conditions or states known as ensembles. Major steps of an atomistic simulation, energy minimization, then relaxation in NVT, and then production run in MPT. And then Jerry here explaining the two main ensembles. Do you want to tell us about canonical versus?
So we have
NPT.
canonical assemblies and isothermal or isobaric assemblies, which are the NPT assemblies. So for the canonical assemblies, we have in the number of particles is constant.
Yes.
The volume is constant, and the temperature is constant. That's why we call it NVT.
Yes.
While for the isothermal or isobaric, the number of molecules particles is constant, the pressure is constant, temperature is constant, but the volume is not constant.
So I'm going to quickly draw here a box. So here, if we draw this box for the NVT, all right, your volume is fixed, so nothing. So this is going to be your X
axis.
Yeah, and this is going to be your Y and your Z. And then you have, exactly, and you have a number of particles in here that are not in any way leaving. So this is why we have a box. So everything is confined. And then the only thing that is changing is pressure. Right?
So you can imagine having like a box and having like apples in a box and everything is sealed. While you are changing the pressure. So the volume is constant, the temperature is constant, and the numbers of apples, which is particles, is constant.
Just want to quickly see something. Good. Yeah.
So you can see.
So when is this NVT used just for the students? So you do that one first, right? Because that allowance of changing the pressure allows you to relax the box.
So it's like having like apples in the box, and then you use like the level of the pressure in the box. The apples have more relaxation states. So if you look at the image we have on the right.
In fact, I'm gonna do this. So I'm quickly gonna, and then sorry, we'll look at. Actually, no, this is the same actually. So sorry. Yeah, please go ahead then. 0, 1, 2. It's actually a very nice image.
So on the right, you can see the flow of the simulation, which is like the general flow for your molecular dynamic simulation. So you can see the system preparation, where we prepare the system, after that we do the energy minimization, then we do the first step of the simulation, which is like the canonical assembly in NVT. Then we do an NPT, then which is the equilibration, and then we do like an equilibrium. And the production run, which is like the long run. So sometimes it might be like, depending on the size of the system, it might take like 2 or 3 weeks or a month of production run. And then we analyze the results.
Louder.
Okay. You want me to say it again loud?
No, it's good. It's good. So I'll just recap quickly. So step 1 that Jerry has, you set up your system in Triangle, right? This is covered in the previous tutorials. And in fact, we need to upload that on YouTube also. I have it already. Then you do a minimization. What is a minimization? So there's no dynamics in the minimization. It's just lowering the energy by moving the waters that are clashing. And depending on your algorithm, you can do a conjugate gradient. And actually, we should kind of have maybe another tutorial on that. Or you're going to do a steepest descent, right? They're different
gradient descents.
So, but there's no time here. I mean, you do steps, but there's no integration of Newton's second law. It's purely an energy procedure where you move along that gradient.
So what happens in minimization is the bonds between atoms or the interaction is being more relaxed. So what we are trying to look for is the lowest energy before we start the simulation.
Exactly, because you couldn't start. If you jump from 1 to 3, the system will very likely crash. So if I'm going to put a cross here, you always got to go first through the minimization, especially GROMACS is very picky and you will not be able to jump. I do not recommend that. Then we have the first equilibration, which is in NVT. It's in Triangle, that will be step 6.1 to 6.3, I think, or 4. And that allows you to relax the box. Typically the volume, the pressure will settle, but the volume will not be allowed to change. But it still is necessary to do that first before we allow the volume then to compress. And that's this NPT. And that's in the NPT, you're gonna see the box lose around 10 to 15%. size. So typically, if we draw it here, oh, just not well drawn, what you're gonna find after your MPT stage is something like this. Gonna find it's going to expand a little bit laterally, and in general, the water, because the water in Changu is deliberately low density.
Yeah.
And then the water is going to compress a little bit. Okay, and then Jerry, you want to tell us about production run? What is production run?
Yeah. So for the production run, we take the equilibrated system that we already have. We run that for a lot of nanoseconds, depending on how you want to sample your system. It can be like 100 nanoseconds, and 200 nanoseconds, and 300, and 500, and you can go as long as 1 microseconds.
Yes.
So what we are trying to do in production is like we are trying to sample the equilibrated system we are trying to sample the equilibrium system where we are trying to see in is it molecular time, or we're trying to sample the equilibrium system at molecular time, and we're comparing the molecular time to physical time.
Yes.
So all you are saying is, let me say, for example, you have ball in the water or like something in water. All you are trying to do here, if you are trying to do the production run, is you are trying to look at what will happen for an actual time of, let me say, 1 microsecond.
Yes.
Of, let me say, for example, ball in water.
Yeah.
So what we try to do is we try to sample that particular physical time.
Yes.
In molecular time.
So the production run, just kind of recap, is for a fully equilibrated system. So you no longer have any changes in the box. Your system is basically ready to look at whatever you wanted to look at initially, and then you run that for a long time to sample the convergence of MD timescales to biological timescales, right? So we have MD timescales, which is at our in femtosecond movement, right? And we got to converge that to biological timescales, which are millis, as Jerry is saying, micro to milli to even to seconds. All right, it's getting a bit messy. I think we move on. Okay, there you go.
So for the initial setup, after the minimization, for the initial setup.
So this is for GROMPP, right? So we gotta explain GROMPP.
Yeah.
So I'm just gonna put a box here. This is GROMPP. So what is GROMPP? What is the GROMPP engine?
So the GROMPP engine is kind of like lines of code built in GROMACS for minimization.
It compresses everything into a single file.
So and the file which is the TPR file. So you can see we have the -O, which is to show for output, -F, which is to show for the file, -C, which is to show for the coordinates.
But this is
so the file highlighted contains the MDP.
So this contains all the MD instructions.
Yeah. So dynamics parameters.
Yes, MD instructions.
So all instructions.
And then I'm gonna go the C are the coordinates.
Yeah.
So that would be from Chamgoy, right?
Which is your PDB file. Yeah.
Chamgoy.
Yeah, CG.
And then R is just a reference file in case you are doing some restraints or some other things. What's the index file?
Well, the index file contains the points or the coordinate points in relation to.
It contains all the groups.
Yeah, and all the groups.
Because GROMACS works in groups. So it might say protein is this atom numbers, membrane if there's a membrane, ions are these, water are these atoms, and it just kind of organizes it.
Kind of like a numbering system for your system, kind of like a numbering system for your system. So it contains like the atom types and the molecule types. So the atoms are like, let me say carbon atoms, you have carbon atoms, and the numbers of carbon atoms you have in your system.
Yes, exactly. And then I think you're also kind of jumping a bit because this is the topology.
Yeah, it's very important.
So
index.
So the topology is essentially the budget file. It tells the program, these are all the types of residues So it's organized by residues, right?
Yeah.
So it says protein, which is not a residue, but that's how it's called. And then it will say the lipids. If you have lipids, each lipid will be spelled out in the number. So if we have here, right, res A, that could be, for instance, POPC.
Yeah.
And then next to it, you will have the number. And it's very strict about this. This has to then correspond to the PDB.
The value.
It's going to count and it's going to check that there's a correspondence. And then you have res B, res C. And GROMACS is going to ensure, basically, is going to check between this file and this file. And if these two don't correspond, it will not allow GROMPP to finish.
So to prepare like the output CPR file,
Yes.
the numbers of atoms in the topo file has to be equal to the numbers of atoms in the PDB file. So if the numbers are not equal, you'll see like missing atoms, like errors like that. So it's very, very important that you like calculate and accurately describe your system in the topology file.
Yes. Luckily, if you're just doing standard stuff, GROMACS, CharmGUI will give you this file.
Yeah.
Okay. And then, oh, this is nice.
Yeah.
Okay.
So this is just kind of like a proper explanation of all relatives in your GROMACS simulation steps. So this is the minimization and this is from. So you can see GMS GROMPP is the preprocessor, preprocessor, the MPP file contains the parameter file, the -o is the output file, the C is the coordinate file, the R is the reference file, which is test VDB or maybe grow sometimes, and the I is the index file, the T is the topology file.
Yeah.
While the final station we have is the max one at all, or
Yes.
100, it's just to continue without warning.
Yeah, it's because GROMACS is a bit picky about the number of warnings. So if you don't have this, then it will not work. Okay, and then so this is just the first step, right? The minimization. And then this, oh, this is nice. So this explains a bit about the topology that we were just talking about, right?
Yeah. Because I feel like the topology file is very, very important.
Yes.
So the topology file, apart from containing the atom types and the residues, it contains references.
Yes, so here we have these are all the parameters that's calling. And these are all the accounting.
Yeah.
This is the budget, as we were saying, right?
Yeah.
And then what's the folder this is referring to up here, right?
So it's referring to a top power folder.
Yes, exactly.
So the power folder contains the ITP on each of the molecules of your system. So if you have, let me say, for example, water with beans, as we said initially, we have to reference the ITP, which are the topology files for beans, the topology file for water, and every other molecules you have in your system. So if it's a membrane, which is POPC, you might have to reference POPC systems, ITPs, if you have like anything mixed. So it's kind of like a reference topology file. So we have like a central topology file, reference to other topology files. So the central topology files do not top.
Exactly.
Reference to top power file.
Exactly. Yeah. So the main file is this. This is a readable file.
Yeah.
It's not binary. And then you have this folder, top power, which contains all these ITV that are also readable. None of these are binary, luckily. And it needs to go through all of this and refer it back, as we said, to the PDB. So it's really going to look at this file and ensure that this accounting corresponds to.
So check the validity of the file system and it compares. That's probably just really.
Yes. Okay. And then.
So this is the MDP file.
Yes, very good.
Which is the dynamics parameter. Kind of like, for example, you want to cook the recipe. So the dynamics parameter contains the constraints, the embos.
Just for the minimization, because you don't want to minimize while it deforms your protein. So we keep the protein fixed for the lipids while we relax things like the water clashes and other things. And what's this EM tool? So the main really parameter is this step. So what does this mean? 5,000 steps of
Yeah.
minimization, right?
So the way the minimization works is you are going down the energy gradient, and as you're going down the energy gradient, we are defining the numbers of steps.
Yes.
We want to move down the energy gradient.
Yes, yes.
Well, to sample.
Well, this is the total number of minimization steps, but then we have this tolerance, which says converge if your energy reaches a convergence less than 1,000, then you would stop. So you won't actually do all 5,000. You'll do as many as you need to get this, and of course this is in units. I believe this is in kilojoules per mole. So for instance, typically when you look at the log file, it will say I did 900 steps, but then it converged. Now, what would be the scenario where it doesn't converge in 5,000? What would be the scenario?
So what will happen if it doesn't convert to 5,000?
But what type of scenario could that be?
So I think if you are if there's like clash,
a huge clash.
So let me say, for example, atoms are overlapping and stuff like that.
For instance, a classical one, right, is that you have benzene ring, right? If you have a benzene ring and then you have a lipid tail going through, this has happened to me before because charm GUI randomly. So if you have a ring and the lipid chain ends up through, this won't be resolved by GROMACS.
So you have to properly remove probably like atoms around your probably like lipid or ligand of interest.
Yes.
To make things more simpler.
So Jerry knows that he likes to remove, say you've added a drug into the box, you will remove, say, the waters within 0.8, what is it, 8 Ohm. Yeah, this is very close contact
of the system.
And these are the restraints. Which again are pretty hard to define if you do them manually, but charm GUI will do it for you.
And this is what really happens when you are doing like an minimization.
Yes, this is what we were just on. 5,000 steps. Just to basically what you were saying. This is the max you will do. And you will just want to stop when. Sorry, so you had already actually explained this. So we can see here, right? So this is where we start and we end here. This is nice.
So there might be like atomic displacements because you are looking for the lowest energy. So and the numbers of lists is kind of like when sampling for the the electrostatic force of the system during the minimization. We are looking at nearby atoms. You don't want to just work on the individual atom because it's an interaction. It's a box, and there will be like multiple interactions that are touching each other constantly. So we are sampling atoms that are really nearby. So that is the number of lists. So you can increase the numbers of lists depending on how you want it. But I think for standard minimization, we do a lot. We just keep it to 10. So and the cutoff scheme is kind of I think it's
the standard.
The standard.
We can look at that more in the. I think this is more important for the next pages. Okay, so we will look at that more for the actual. But this is nicely explained. Okay. So this is the force field, right? So you have your force field here. And we did, just for the students that are online, we did cover force field in the previous tutorial. This pretty much explained very nicely here that we do max 5,000 steps, but we start with the tolerance, basically what you have here, right? And as soon as you have your energy tolerance, you'll stop. Oh, okay, very nice. So
you can see there's like a clear description of what we do. First, we compute the energy at the forces to make sure like the system is correctly set up. Then we do like relaxation, which probably might lead to atomic displacement. Where we have said, the atoms at high energy potential. We are looking for the lowest energy for the atoms. We search with the neighboring lists. Then we move from one step to the other with the set.
And in the previous tutorial, I had videos of the output of the molecular dynamics. And I think we will do another recording with the other steps. So thanks guys for joining us, and see you next time.